Assalamualaikum everyone. Now we are going to moving towards another lab, lab number 7. This lab is one of the very fundamental and important lab in order to understand the time domain specifications. As you already have gone through the preliminaries of system modeling, mechanical modeling, electrical modeling, and you have learned how the ODE solver solves these equations to get the desired response across different systems. Now, in this lab, we are actually going towards understanding one of the two very important systems. So, in that case, you guys can uh, understand that the control system theory basically you can say has two parts. One is the its number one is its dynamic part, and number two is its control part. So in if you want to understand the dynamic part, it is very important that you understand the fundamentals of at the first position how first order systems work, and then you need to understand how second order system work. So in this lab we are going to understand both the system and practically getting how the system behave with respect to the selected time domain specification parameters for each of the individual systems, that is for first order systems and for second order system. Let me briefly discuss here what we are going to perform in this lab. We will be looking out the performance of first order and second order system and develop the domain specification functions. It means in order to control the output, whether your system is a first order system or a second order system, you have to understand what are the required time domain specification for the first and second order system. So how we will go through the first and second order system. In the start, we will be going through the first order system. A simple RC circuit can be treated as a first order system, and in that case, the first order system is that in which we have a single pole in the equation, and then first I will show you how we can develop this first order system from these equations, and then how can we actually plot that first order system and what are the time domain specification parameters for that system. So because you have already been going through the MATLAB and simulating exercises, and in the live interaction I'm going to discuss with you in details. So let's have a brief introduction of this any of the chosen first order system. Here you can see that first you need to find out the transfer function of this first order system. For example, this is your RC circuit where there is a power supply connected. For example, just a minute, a power supply connected, you can write down by using a certain source here, plus and minus, and then you can give some, for example, this is your V in, and the voltage across capacitor could be your V out. So in that first order system, you can do either voltage across capacitor could be V out, or you can see the current across the loop could be your output. So anything we can do it. You can do another exercise by taking this. So right now we take voltage across capacitor as your V out. So by applying KVL, what we get when we apply KVL, apply KVL across the loop, what we get? We get V input voltage is equal to the the voltage drop across resistance, and the voltage across capacitor, that is VC. Note that VC is equal to V out, where this could be your V out, and in that case V in, because your VC is V out. Now what we know that in this case I is equal to IC is equal to IR, so I can directly write that I current across capacitor is equal to CdVC. So here CdVC, just give me a second. Yes, it is actually the output. So here we can see CdVC can be treated as D can be replaced as a Laplace operator, because the initial conditions are 0. So we can see IC is equal to CSVC. So in that case, I can directly put the value of IC here. So it becomes RC SVC plus VC, and then I can take RC as a common. So it comes out to be, no, not now. I can later take it as a common. Right now I'm just taking VC as common, and it comes out to be RCS plus 1, and then this is Vn. Now the output Vc upon input Vn, which is your system transfer function in the first order case, first order transfer function Vn, what you get is 1 upon RCS plus 1. Now further simplifying this scenario here, I'm taking it towards the right side. So your transfer function is actually becomes, for example, if I divide numerator and denominator with RC, so it comes out to be uh, S upon 1 upon RC. So let's suppose, let we define A is equal to 1 upon RC, and which is equal to the time constant tau, that is 1 upon A, or you can say simply RC. So in that case, the important parameter that we get, further simplifying, or you can say the putting the values of transfer function equal to A upon S plus A. So this is, you get a first order system from this RC circuit, in which tau is the parameter. As we all know that the tau is the system characteristic parameter, which tells that at a particular system at its certain time tau achieve the 63% of the desired output at that particular time. So the one of the characteristic parameter, time domain characteristic parameter, could be a 1 upon 1 could be tau. Another time domain parameter could be, for example, if I plot this parameter, this is my desired output, and if I plot this, so it comes out to be something like this. So at this point, when it gives 63% point 63 point something percent of this value, this value is usually its tau value. So but we have another two different parameter. The one parameter is its rise time, and that rise time is usually, according to the definition, it becomes TR, and the formula of TR is 2.2 upon A. You can drive it. And you have another parameter that is called system settling time, TS, and this definition of settling time could be 4 upon A. So for any system you can find out tau, rise time, and settling time. Based on that, you can you can these all values depend upon tau depends upon a, 1 upon a. Rise time depends upon also 2.2 time upon a, and settling time depends on 4 upon a. So basically, by changing the value of a, which represents the system physical parameters, you can change the response. So in this lab, what you are going to do, you have to just make this transfer function, and I will tell you at the end of this lab how to make the transfer function. But it is very important to first understand the concepts. So when you understand the concept, then it is very easy. So you make a different transfer functions, and by changing the values of a, you can get a different value of rise time, different values of rise time, settling time, and tau. So this will be your first task in this system. Now I'm gradually moving towards the second order system. If somebody asks you what are the domain specification of the first order system, then you are going to tell that tau, the rise time and the settling time in case of the first order system. Now, if we talk about the second order system, simple RLC circuit can be the type of the second order system. But now let's change little mood, and we will be taking the example of control system theory. Over all the course of control system theory, you have been solving this problem. Let's see what is the input. Input seems to be to me as f, and x seems to me as the output. So we already have this particular transfer function, and that transfer function can be compared. That transfer function actually can be compared with the standard form. That is the second order standard form. Remember one thing: whenever you have a transfer function in the form of a physical parameters, then what happens that every time when the system dynamic connection changes. What does that mean, dynamic connections? When the system dynamic connection means, for example, the spring is attached with another mass in series, or when the damper is attached in series with the spring, for example, this could be the another dynamic connection. Let's see, let's take another example here. I'm talking about right now here second order system. For example, you get a spring, and then you get a damper here, K and B, and then you get a mass. So it is still a second order system, but the equation will be different from this second order system. So every time you don't need to remember that what kind of equation you are going to get. For example, in this case, you have been getting the equation in this case when spring and the damper are connected in parallel, in parallel to the one node x attached to the mass, and the other node with the reference, and force F is pulling that mass. So in this case, the transfer function comes out to be F is your output and X is being your input. So this could be the transfer function in our case. So now what you are going to do, you are just comparing these two equations. So when you compare these two equations, then you get different time domain specification responses. Now let me draw something very good for you here. Just give me a second. For example, this is your case when you are, yeah, okay. So this is your case. Let's see, heading second order system, because this is mean you have done multiple time system. So your transfer function, second order transfer function comes out to be, for example, 1 upon, this is your output is xs, and input is fs, which I have noted previously, is equal to, you don't need to worry about it. I have a, just give me a second. I can remove this part especially. Okay, so when you have a transfer function something like this, 1 upon m s square plus bs plus k, what you can do, you can divide, and you can divide this transfer function with m on both sides. So if you divide it by m on both sides, then this comes out to be like s square plus b upon ms plus k upon m. And you already know the standard, like previously you have seen a upon s plus a, the being the standard form of first order system. The standard second order system equation, that is standard second order system equation of transfer function is omega n square upon s square plus 2 zeta omega n s plus omega n square. Probably the manual is using, yes, it is also using the same criteria. So what you have to do, let me tell you, what you have to do is you have to compare these two equations. When you compare these two equations, what happens, comes the omega n. Yeah, if you compare these two equations, omega n comes out to be under root k upon m, and zeta comes out to be b upon 2 under root mk. You can directly, by comparing these two equations and substituting the value of omega n being under root k upon m, you can do it. Now for different values of zeta, that actually that those are actually dependent, on b and mk. For example, if I want to make a zeta greater than 1, which is the typical case of overdamped case, which is a typical overdamped case. So what you do, you will try to keep b greater than 2 under root mk. You will select those values of mk so that b is always greater than mk. For example, if you want to make zeta equal to 1, that is the case of critically damped. Okay, in that case b must be equal to 2 under root mk. For example, if you want to make zeta equal to less than 1, for example, less than 1 but not less than 0, so in that case system response is underdamped, and when the system response is underdamped, then b must be less than 2 under root mk. And for example, you want to make zeta equal to 0, that is the case of undamped. This is underdamped, that is the case of undamped. In that case, b is equal to 0. That is only possible when zeta is equal to 0 by substituting these values. So in this lab, what you have to do, you have to get the time domain specification of a second order system. So what does that mean? Like in second order system, we will be selecting this case, the underdam case. Why we are selecting this and why we are having the experiment of this case specifically? Because this is the fastest of all the cases. That is why we have chosen only the underdam case. Only the underdam case. Let me highlight it so that you guys can remember it. So that will only be the this one case. So we are only talking about this. It means we will be choosing the value of zeta between 0 and 1. So what kind of time domain specifications we have? Let's draw this kind of response usually we have in case of underdam. Okay, so when we have this kind of response, then what happens? Then in this kinds of response, you have let me use the opportunity of drawing with different markers. Okay, for example, this becomes your system rise time. This is your first time domain specification tool. This becomes your system peak time. This is your second number time domain specification parameter. Now let's see, this becomes your system peak output. This is your third parameter. This ratio is your mp, m naught, like equal to percent overshoot. And the fifth, not never the least, the settling time, it could be of two standards. Number one, settling time when the error is 5%, and the error is 5%, and another settling time when the error is here somewhere is equal to TS equal to 2%. So you can say your fifth specification parameter has one for 5% and second for Roman. In Roman, I would like to write it. Since settling time for 2%. You guys can do what you guys can do in this lab. You have to write a transfer function, and in this transfer function, basically you have to find the rise time, peak time, settling time. You already know the formulas, and not all the formulas are given. I will write it for you here. But what you have to do, you have to fill this observation chart by putting the different values of zeta in your transfer function, and by different value of zeta between 0 and 1, because we have chosen underdamped case. So you will make you will select m and k differently in such a way that the value remains within 0 and 1, and those value would be zero point 0.1, zero point 0.4, zero point 0.7, and 1.0. And then you will calculate the rise time, peak time, overshoot, settling time, and steady state error. And then you will, by using the command of a step response, you can solve it. So I'm writing here the formula for you of these five time domain specification parameters. Number one, rise time, that is phi minus cos inverse of zeta divided by omega n under root 1 minus zeta square. Okay. Number two becomes peak time. Peak time become pi divided by omega n under root 1 minus zeta square. You already know the omega n. Okay. Number three, you can get Cp. I guess Cp is 1 plus exponential minus zeta pi upon under omega n. So not omega n, sorry. 1 minus zeta square. And the number four is percent MP, percent overshoot, you can say. And in the percent overshoot, you only have the above formula uh, without 1, and that is 1 minus zeta square into 100%. And the fifth one has two part. I can rephrase this as A and as B. Okay. So in the A part, fifth one is settling time, and settling time for 5% is 5% is 3 upon zeta omega n, and settling time for 2% is 4 upon zeta omega n. So these are the values you can draw and fill the table. So whenever you want a desired output, so what you actually set these time domain specification parameters. The other queries and details can be asked in the live interaction. So now I'm going to tell you a bit more related to the how you will going to implement it in a MATLAB. So you already have understood that how to create a transfer function in the MATLAB. Probably the previous slides or lecture labs in the introduction of MATLAB, you have already learned how to draw the how to obtain a polynomial function in MATLAB. In our case, we are using I'm going to highlight here something. We are going to use a very simple commands here to draw the transfer function. For transfer function, what we are going to do is we will be using this command. Remember, only this command. We will select s is equal to transfer function as symbol, and then after that what we are going to do is write a numerator, and write a denominator as an array, and then we will say system is equal to transfer function numerator comma denominator. In that case you will get this kind of transfer function. Once you have this transfer function, you can change different values of zeta here in bracket, for example, and then you can just write step sys. Step sys will give you the system response, and at the once you get a step sys response, then you will get this kind of response. After clicking right, you can just directly calculate the rise time, settling time, and mm, peak time and overshoot. Similarly, same is the case with the first order system. I'll be discussing this in these when you will be with me in the live lectures as well. So this is it for the first and second order responses specification. I'm just going to summarize it for you here, that we have learned right now two type of system. One is the first order system and another is the second order system, and we learned about the dynamical control of that system. Here what we learned, that in the first order system there are three kinds of time domain specification, and in the second order system we also have a talk in this, but we don't need to represent it here. So specifically we selected it the underdamped case, and we solved it through time domain specification. I'm hopeful you have guys have learned in this. And in the next lecture I'm going to give you a lecture on the PIDs. Thank you so much.